Hi all. Last day we have discussed what is the meaning of covariant derivative, and up to this point we have discussed uh, alpha is a geodesic in S if and only if its covariant acceleration is zero along alpha. Uh, this is a trivial thing. When the definition of geodesic is acceleration is always perpendicular to the tangential field, or that is in the direction of the normal vector field. So that is the definition of the geodesic. That means alpha dot is always a multiple of c times n of alpha of t. This is the requirement of the definition of geodesic. When you consider this covariant derivative of alpha dot, covariant derivative of alpha dot is defined as usual derivative of alpha dot minus the normal component of the alpha dot in the normal direction. So that is obtained by taking the dot product with n of alpha n times this n again. So this is when we take this is the covariant derivative of the velocity vector field, that is the covariant acceleration. So when this is equal to 0, if and only if we can say that alpha double dot is in the direction of n. Okay, that is a normal vector field. So this proves alpha is geodesic if and only if its covariant acceleration is 0 along alpha. Now we define parallel vectors. We know that in our Cartesian coordinates or Euclidean geometry, you can say that two vectors are normal if it's usually a vector has two parts. In case of R2 or in Euclidean space, one is the magnitude of that, and next is the direction. If the directions are same, we can say that two vectors are parallel in our usual sense. So we can adopt the same thing in this definition, Euclidean parallel vectors. If we define two vectors, v is equal to pv and w is equal to qw, this v is a vector at the point p and w is the vector at the point q. If the vector part of these two quantities are same, then we can say that v and w are parallel. In fact, Euclidean parallel. Okay, so Euclidean parallel vectors in our definition is defined as v equal to p comma v, w is equal to q comma w with this vector part v is equal to this w. Okay, then we can say that these vectors are Euclidean parallel vectors. So that means if this is the case, we can say that at every point these vectors are parallel. Okay, at this point, if this is p1, p2, p3 and all, we can say that this is some v1, v2, v3. These are all same, right? So p1v, p2v, all these vectors are parallel vectors. So these are parallel Euclidean parallel vectors. So this is the definition of Euclidean parallelism. A vector field x of t along alpha is Euclidean parallel if and only if this x of t assigns parallel vectors at every point. Okay, so that will be x of t equal to say some alpha of t comma this is some x of t, x of alpha of t. If this x of alpha of t is constant for every t, we can say that that vector field is Euclidean parallel vector field. That means Euclidean parallel vector field assigns parallel vectors at every point of the domain of the vector field. So this is the definition of parallel Euclidean parallel along alpha. Okay, this is if and only if x dot is equal to 0. Okay, x dot equal to 0 means these components are if this x of alpha of t is 0, that means x1 of alpha of t equal to 0, derivative of this is equal to 0. X dot is defined as the components of derivative of the components of this x. So that is when you define this, you can say that this derivative equal to x2 dash of alpha of t etc. are all 0. Then in particular x dot equal to 0. X dot of alpha of t equal to 0 for every t, we can say that this x dot is 0. That means x is Euclidean parallel along alpha. So this is the definition of Euclidean parallel vector field along a parameterized curve alpha. Now we define another concept of parallelism. So that is what we called Levi-Civita parallel vectors. Okay, parallel vector field along alpha. That is obtained by defining x prime is equal to 0 rather than x dot equal to 0. Okay, that means x prime equal to 0 implies the covariant derivative of that vector field is 0. So the covariant derivative defines only when this x is a tangential vector field. That means x dot of alpha of t is in the direction of normal vector field. That is, this is x dot of alpha of t dot n of alpha of t times n of alpha. Okay. So this is the definition of x prime. When it is 0, we can say that this is same as this one. The definition is this minus this one. So we can say that the this is equal to 0 means the normal component. Actually, we are projecting this x dot to the tangential plane. So if this is equal to 0 means then we already suppressed it in the tangential space. Tangential space is 0 means the component corresponding to tangent space is 0 means it contains only normal component. Okay, so this x dot is in the direction of the normal. So this is the requirement of Levi-Civita parallelism. The tangential vector field x, this belongs to S of alpha of t. We can say that this is a Levi-Civita parallel vector field. So a tangential vector field along alpha is said to be Levi-Civita parallel vector field or simply parallel. Okay. Now onwards we call this is the parallel vector field. If this happens, the derivative of that tangent vector field is always, usual derivative of that tangent vector field is always in the direction of n of alpha of t. So that means when you consider this type of a curve or a surface, then the Levi-Civita parallelism, these are the tangential vector field at this point. If we consider the derivative of this, okay, if the derivative of this is in the direction of the normal at this point, we can say that sometimes this will be like this. We can say that this is Levi-Civita parallel vector fields, because when as you move along this curve, when you look up this x dot, so that can be seen in this direction. Okay, so there will not be any change in this corresponding to this vectors. So if that means the normal the tangential component of these derivative vector field, this is the tangent vector field, and if this is the derivative vector field, then the normal component, there is only normal component, there is no component along the tangential space. Okay, so if this is the case, we can say that this x prime or x, the tangential vector field x, is Levi-Civita parallel. Okay, so the only thing is there is no tangential component for this usual derivative. So that means the usual derivative is along the direction of the normal vector field. So this is the only this is the geometry of the Levi-Civita parallel vectors. There are a number of remarks on this Levi-Civita parallelism. If x is parallel along alpha, this parallel means Levi-Civita parallel, then x has a constant length. Since when you take the derivative of the scalar vector field norm x square, that is d by dt of x dot x, that is the usual derivative of this. We can write this in terms of covariant derivative, as we have discussed already the properties of the covariant derivative. So that is x prime dot x plus x dot x prime, so that is 2 times this. Since this is Levi-Civita parallel, this quantity is the covariant derivative is 0, so this dot product is 0, so we can get this one. The second property is if x and y are 2 parallel vector fields, that is Levi-Civita parallel, covariant derivative is 0, then x dot y is a constant along alpha. Since if you take the dot product of this and taking usual derivative, that can be expressed in terms of covariant derivative. Since these two vector field x and y are parallel, then covariant derivatives are 0. then you can get this dot product. Derivative of the dot product is 0. Okay, that means x dot y is always a constant scalar function along alpha. The third property is x and y are parallel along alpha. Then the angle cos inverse of this between x and y is constant along alpha. Okay, because this cos inverse of this is defined in terms of x dot y and norm x and norm y. We have already seen that x and y are Levi-Civita parallel. Then this is a constant, and these two quantities are constant. So cos inverse of this this bracket is also constant. Therefore, we can say that the angle is constant. Okay, now we have the fourth remark. If x and y are parallel along alpha, then so are x plus y and cx. Okay, this is nothing but the usual properties of the covariant derivative. This x, y primes, this will be 0. This is nothing but x plus y whole prime. So these two x and y are covariant derivative, x and y are parallel, then these two derivatives are 0. Consequently, x plus y, the current derivative of x plus y is also 0. Similarly, you can prove that cx is also parallel. So sum and scalar multiples of the parallel vector fields is always parallel. Now we have the fifth property. The velocity vector field along a parameterized curve alpha in S is parallel. That is Levi-Civita parallel. That is covariant derivative 0. So this part is nothing but the covariant derivative 0. If and only if alpha is geodesic. Okay, we already discussed in the beginning session of this lecture. Alpha covariant derivative 0 if and only if the velocity x, the covariant acceleration is 0. So this proves these are the 5 important properties of the covariant derivative. Next we will discuss the theorem on this covariant derivative in the next class.